Good morning everyone. Today we will discuss some examples of recurrence, how to solve recurrence. And for solving recurrence, there is an important and simple tool called master theorem. This master theorem is applicable for most of the recurrences. जो recurrence master theorem के general formula पे fit बैठते हैं उनके लिए ये बहुत अच्छा है. तो सबसे पहले तो जो master theorem है उसका स्टैंडर्ड फॉर्मेट क्या है? The standard format of master theorem is suppose any recurrence relation is written as Tn is equals to A T n by B plus Fn. Tn is a recurrence function. In right hand side, A is a constant which is greater than 0. Then this lower recurrence term Tn by B plus some function Fn. And this Fn is independent of recursive term of Tn. Then there is a simple method to solve this. And I am quoting this method. First, we have to calculate the logarithm of A base B. Then take the power of this. And this is compared with the non-recursive part. I am just explaining a little bit. This recurrence function or recurrence relation having two parts. This one is recursive part. This one is non-recursive part, non-repetitive part. So we are here to determine the amount of effect on algorithm complexity. Which one is greater? Either this recursive part is more giving a stress on time complexity, or this non-recursive part is giving. This only simple master theorem explain this. But without going into too much detail, the simplest method is to solve this master theorem like this one. And then this is compared with this function. Based on the comparison result, there are three cases. Why three cases? Either this n to the power log of A base B is greater than Fn, or this n to the power log of A base B is equals to Fn, or this n to the power log of A base B is less than Fn. There are three cases. Either this is greater than or equals to or less than. Based on three cases, there are three quick formula are given for complexity. I am just coming to an example and stating the example, solving this example, I will explain this master theorem. The first recurrence relation is given as Tn is equals to 9Tn by 3 plus n. Comparing with the standard format of master theorem function, the value of A is 9, the value of B is 3, and the Fn is equals to only n. Now, according to formula, first we have to calculate log of A base B. That means this is equals to log of 9 base 3, and this comes to be 2. Now taking power of this n square. Now this is actually n to the power log of A base B, and this is compared with the function Fn. Fn is n. Naturally, in this given example, n square is greater than n. This logic only reflects that the recursive part is giving more stress on the complexity. The recursive part is more influencing the complexity. That means that the solution of this recursive function is Not going into too much detail, the solution of this is theta of n square. If I am quoting this statement in very formal way, then this statement is to be written like log of a to the base b n, and this is fn. Suppose a very small positive quantity is subtracted from this amount, and if this is equals to fn, this equation reflects the fact that n to the power log of a base b is more than fn. This means the solution is theta of n to the power log of a base b. It is written formally. What I am quoting in solve example, I am writing it again formally. Now for the second one. For the second case, suppose n to the power log of a base b is equals to fn. Then the solution is Tn is equals to n to the power log of a base b log n. And the third case, I am just quoting here. Suppose a very small positive quantity is added here. This equation reflects that fn is little more than n to the power log of a base b. Then fn is influencing much more than the recursive part. Then the Tn is equals to theta of fn. These are formal definition. Now I am coming to the example, solving the example. The first example comes under the case in which n to the power log of a base b is a little more than fn. Now for the second example, in this example, the recurrence relation is given, and comparing with the standard format, this will be constant a, this will be constant b, and this is fn. Now the same logic. First we have to calculate log of ba, which is to be log of a to the base b is log of 9 to the base 3, again comes is to be 2, taking the power and comparing it with fn. Now the case 2 arises, in which log of a to the base b, n to the power log of a to the base b is equals to fn. Then the time complexity Tn having the solution of theta of n to the power log of a base b, exactly this one, n square log n. Now coming to the third example. This one. Coming to the third example. Tn is equals to n 9 t n by 3 nq. This is again a, this is again constant b, and this one is fn. Now log of a base b is equals to log of 9 base 3 is equals to again 2, again n square, and it is compared with fn, and this comes to be nq. Now in this case, this is the third case. In this case, fn is greater than n to the power log of a base b. Then the solution will be Tn is equals to this one. And this is the simple method. I'm also coming to the next example. This one. Now here is A, here is B, here is Fn. Now A is equals to 3, B is equals to 9, and Fn is equals to linear n. Then the log of A to the base B is equals to log of 3 base 9. And how much it is? It comes to be little less than 0.5, 0.5. I'm approximating this one. Now the power of it is compared with Fn. Now n to the power log of A base B is less than. Then the Tn is equals to theta of Fn. Again, coming to next example. Tn is equals to T 2n by 3 plus theta of 1. That means here A is equals to 1 and B is equals to 3 by 2, because I am counting B as a denominator, and Fn is equals to theta of n. I am just writing here. In this example, the value of A is 1. The value of A is 1. The value of B is the denominator, and which is 3 by 2. And Fn is equals to theta of n. This theta of n reflects that there is a constant function. Constant function means the function having variable power 0. That means n to the power 0. So all are equivalent or interchangeably in complexity example, like theta of 1 is written, theta of k is written, theta of n to the power 0 is written. All are same in terms of complexity. Now taking the same formula, log of A base B. This means log of 1 base 3 by 2, and log of anything, any base with log of 1 with base anything is 0. That means n to the power 0. Again it is compared with theta of 1, and these two are equal. These two are equal, then the time complexity of or solution of this recurrence relation is Tn is equals to theta of n to the power log of B base A. Log of B base A is n to the power 0. That means constant 1 into log n, and this comes to be log of n. Now I am coming to next example. Again, taking a quick analysis of this. In this case, A is equals to 7, B is equals to 2, Fn is equals to n square. Now, A is equals to 7, B is equals to 2, Fn is equals to n square. Now, log of a base b, and this comes to be how much? 2 to the power 1 is 2, 2 to the power 2 is 4, and 2 to the power 3 is 8. That means something in between 2 and 3 and close to 3 approximately. I am counting this one, 2.8. Now, n to the power 2.8 is compared with n square. Clearly this log of a to the base b, n to the power log of a to the base b is little more than fn. Then the solution of this recurrence is theta of n to the power 2.8. Now for the next example. Again, here a, here b, here fn. A is equals to 16, b is equals to 4, fn is equals to n square. Now, log of a to the base b is equals to log of 16 to the base 4 is equals to 2. Now, n square is equals to n square. Then solution of this recurrence is n square log n. Coming to next example. Here the value of a is 1, the value of b is 10/9. A is equals to 1, b is equals to 10/9, only denominator, and fn is equals to n. Now, log of a base b is equals to log of a base 10/9. That comes to be 0. That means and 0 is compared with fn. Now fn is more than n to the power log of a base b. Then the solution of this recurrence is this one. And now coming to the last example written here is 70n/3 n square. That means a is equals to 7, b is equals to 3, and fn is equals to n square. Now log of a base b is equals to 3 to the power 1 is 3, 3 to the power 2 is 9. That means in between 1 and 2, and just approximating this is like 1.6. Now it is compared with 1.6 to n square. Clearly the fn is more. Then the solution of this recurrence is theta of n square. In solving recurrence, recurrence means something in left hand side, something is left hand side is dependent upon something on right hand side plus some non-dependent part. I am giving the logic behind this. This is some recursive function, a part of a partial recursive function is there, means this is dependent upon this and for some independent. In any algorithm analysis, this equation comes after summing of the number of steps or number of instruction or time taken by individual instruction. This function arises. ये फंक्शन मुझे तब मिलेगा जब मैं किसी एल्गोरिदम में n इनपुट यहाँ पे साइज भी हो सकता है, नंबर ऑफ इनपुट भी हो सकता है, बोथ द केसेस, और उसको सम करते हुए किसी एल्गोरिदम के सारे इंस्ट्रक्शन के फंक्शन को सम करते हुए जब मैं इस फंक्शन पे पहुंचूंगा, इसे कहा जाता है रिकर्सिव फंक्शन. ये कोई जरूरी नहीं है कि हर बार रिकर्सिव फंक्शन हो. रिकर्सिव रिलेशन या फंक्शन तभी मिलेगा जब एल्गोरिदम रिकर्सिव हो. फॉर एग्जांपल, सम एल्गोरिदम इज एल्गो ए of n input. Now some instructions are written and this same algorithm is calling itself with some lower input. Some instructions are there and it may be now. At a simple overview of this algorithm having some independent instructions, and these independent instructions are also have some computation time on machine, and in between these instructions or in the body of the algorithm there is a statement in which this algorithm is called itself with the lower amount of input. It may be anything 2n by 3, n by 7 or whatever lower term, and again it is calling this one. If we analyze this algorithm and summing up all the instruction, this comes to be as a function of, suppose Tn, because the number of input here is n, suppose Tn is the time taken or total number of steps of whole of the algorithm, then this Tn will be written as Tn is equals to a recursive term Tn by 2 plus some non-recursive instructions plus some recursive term Tn by 2 plus some non-recursive instructions. Now rewriting this, Tn is equals to 2Tn by 2 plus some non-recursive instructions. This non-recursive instruction may have some linear power of n, logarithm or square power, whatever may be. Now in analyzing the complexity or the solving Tn means analyzing the complexity, the solution of Tn will be influenced by either recursive term or non-recursive term. And in the master theorem, we calculate only this. The n to the power log of a base b is total amount of influence given by this recursive term. And this Fn is total amount of influence given by non-recursive term. In master theorem, we compute the amount of recursive influences and also Fn is given directly. Then we compare these two. If recursive term is influencing more, then overall Tn will be according to recursive part. If non-recursive part, that is Fn, is influencing more, then overall solution of Tn, that means overall influence is given by Fn. This is the concept behind a master theorem. So logically, in all the example, this is recursive part, this is non-recursive part, this is recursive part, this is non-recursive part, this is recursive part, non-recursive part, recursive part, non-recursive part, and in previous example also, this one is recursive part, non-recursive part, recursive and non-recursive, recursive and non-recursive, recursive and non-recursive, recursive and non-recursive. So this master theorem is very useful in most of the cases in which the given recurrence function, after computing the total time of the instruction or sum of the instruction, if the equation arises in the form of recurrence relation, it will be solved very easily. There are other methods also, like recursion tree method, in which this recurrence relation is expanded and solved. Also there is a method substitution. In this case, the recursive term may be substituted by different lower term. But if the standard format is like this, Tn is equals to A Tn by B plus Fn, then master theorem gives accurate result. Thank you.